Here we go. So organized troubleshooting is knowing the system. What is it supposed to be doing? Got to listen to your customer. Their observations are important. Ask them what it's doing, when it's doing it. You know, sounds it's making, temperatures, that kind of stuff can all be pretty helpful. Use all your senses, look, touch, smell, listen. That's a big thing I use when I go in to diagnose something is feeling it, you know, putting your hands on it, seeing what's cold, what's hot, what's supposed to be cold, what's supposed to be hot, that kind of stuff. Be logical and analytical, use an if-then thinking. If this, then that, you know, that kind of thing. Get input from other techs or the manufacturer. A lot of times other techs can be a good resource for you, sometimes even better than the manufacturer if they have experience with that stuff. We've got a lot of guys in the company that know quite a bit of, you know, good information about things like this, so definitely use your resources that are available to you. Sometimes tech support's a little hard to get a hold of. You want to find the cause. It's usually just one main problem. A good tech will ask why. Parts changers, just keep chucking parts at it until it works. You want to give an estimate first. Is it worth repairing? You know, customers like Maverick, they're big on that. They have a kind of a rule of thumb. If it's 10 years old or older, or if the unit's just beat up, most of the time they'll go with the replacement. Some of our other customers, you got to be a little bit more ginger about it. You know, just tell them, hey, that piece of shit needs to be replaced. You know, maybe go about it a little differently. But 9 times out of 10, if you present yourself professionally and give them a good reason of why you think it should be replaced, if they can afford it, 9 times out of 10 they'll do it. What is normal for air conditioning? A 30-degree condenser split. For 10 SEER standard units, high efficiency units is 15 to 20 degree split. That only applies when your outdoor ambient is 70 to 100. A lot of those charts you can find online if you don't have access to them. 10 degree subcooling is average. 5 to 20 is okay. You want a 35 degree evaporator TD. I don't know how many of you have those Fluke, I can't remember the model number, but it does 2 temperature readings at once. They're a little pricey, but they're really nice for taking TDs across condensers and evaporators. It does it all for you, and it's a live reading, so you're not taking one reading on one side and the other reading on the other side and then trying to add them together. With your 10 degree evaporator superheat, that's what we're looking for. That's an average. 5 to 20 is okay. Your suction line temperature taken close to the evaporator outlet, as close as you can get, you know, anywhere not on a weld or on a fitting or anything like that. This is a normal AC system, 10 CRR22. The condenser split's going to be a 30 degree with an ambient air of 95. That'll make your condenser temp 125. Subcooling 10. Everybody understand how they get to that? It's pretty simple. With an evap TD of 35 degrees and a return air of 75, that'll make your evap temp 40. With a 50 degree suction line, that gives you a 10 degree superheat. Now your procedures for troubleshooting: first, want to determine the conditions for the evaporator temperature, the superheat, the condensing temperature, and the subcooling. Second, decide if each condition is normal, or if it's high or if it's low. It's a good way to differentiate what the problem is and what direction you need to be looking at. Your evaporator temp, normal evaporator temperature, or normal evaporator TD for that system, Temperatures may vary, but the TD should not. You should always have the same temperature differential. A high evaporator temperature or high pressure flooded evaporator or high load. Low evaporator temp is low pressure or starving evaporator or low load. Normal evaporator superheat is about 5 to 20, the suction line temperature taken at the evaporator outlet. A high superheat or starving is over 20 superheat. Refrigerant is vaporized too early in the coil. It would make your liquid line a little warm as well. You can kind of go off of touch with that one. Low superheat or flooding is under 5 degrees. Refrigerant is not fully vaporized leaving the coil. Technically, 1 degree of superheat indicates vapor, but saying under 5 allows for some. Let's see. Allows for some instrument error. The high superheat fixed metering device. Fixed metering devices can't maintain a superheat. They cannot adjust the refrigerant flow as needed. A high superheat will indicate a starving evap or refrigerant not filling the coil. Causes of that can be a high load, refrigerant is boiling too quickly or undercharged, or a restriction in the line. On these train units that use a fixed metering device, there's a lot of those that they do get plugged up. If I remember right, Trane still does sell a flush kit that works pretty well to correct that problem. The key to diagnosing a high superheat is your evaporator TD. It's one of the big indications of it. You have a high load with an 80-degree suction line and a high superheat of 30 degrees. Your return air is 85. You have a normal evaporator TD and a normal evaporator temp with a high superheat. Kind of indicates a low charge. Thanks, man. You want me to put this up on the TV so you can see? Just a sec. I got to get this up on the TV for some people here in the class. At 85 degrees return air, the evaporator should be 50. So it is running low. Low evap temp, high superheat. A low superheat with a fixed metering device. The fixed metering devices don't maintain, they just do what they're doing. They have no fluctuation. A low superheat is a flooded evap or too much refrigerant in coil, low evaporator airflow, refrigerant not boiling off. A high condenser pressure or pushing refrigerant through the evap, low condenser airflow or overcharge. The key to diagnosing the superheat is once again the evaporator TD. You can tell a lot from how your evaporator is behaving. Fixed metering devices cannot regulate the refrigerant flow. It's just a piece of metal with a hole in it. Factory designed for a fixed pressure drop based on application and refrigerant used. So depending on what kind of gas they're using in the application, it's the orifice size will be a different, smaller or larger diameter. What happens when your head pressure rises? The evaporator pressure and temperature also rise. What happens when the head pressure falls? The evaporator pressure and temperature also fall. So they're linked together. Two popular types of fixed metering devices are a piston. It's primarily used in air conditioning, or capillary tubes, primarily used in refrigeration. We see cap tubes a lot on prep tables, our favorite thing to work on. With an overcharge, you're going to see high pressure up at your suction line, evap temp 60, 80-degree return air at the evaporator should be 45. So we're running way too high. 60-degree suction line gives you 0-degree superheat. There we go. Iced up evaporator with a fixed metering device. Hang on. There we go. Evap TD of 50, way too high. 80-degree return air, the evaporator should be 45. So 30 is a little too low. 0-degree superheat, once again, low evap temp, low superheat. Now it's talking about an evaporator superheat with an expansion valve. Expansion valves will maintain a normal superheat under small load variations. They will not maintain a superheat when very low load, a dirty filter, dirty evap, low airflow, will give you a low superheat. A very high load or a hot pull down, if you've got a unit that's in a kitchen that's got a lot of heat coming up into the return air, you can have problems with that. Or a low charge can give you a high superheat as well. Condenser operation, the condensers reject the heat from the evaporator. The more evap heat, the higher the condensing temp. The less evap heat, the lower the condensing temp. Condensers also reject sensible heat. Superheat from the evaporator and suction line, the compressor motor heat, and heat of compression. Normal condensing temperature based on a condenser split designed for that system. Condenser split equals the condensing temp minus the ambient, or the condenser split plus ambient equals your condensing temperature. In a normal AC condenser operation, the Tenseer R22 with a fixed metering device, you got an ambient air of 95, return air of 75. Oh, hang on. Normal operation, you've got your evap temp of 40, superheat at 10, everything looking good, subcooling's looking good. So that's what you want to see. The condenser subcooling, normal subcooling is going to be 5 to 20, like I said earlier. High subcooling above 20 degrees, overcharge or non-condensables. Non-condensables are not a very common thing to find in the system, at least if it's on a place that we've been working on. Hopefully our guys are all doing proper evacuations and anytime they're opening a system and recharging, so won't really run into that too much, hopefully, but it does happen. Low subcooling or under 5 degrees is going to be an indication of a low charge. Causes of a low condensing temperature, low charge, low load, low ambient, under 70 degrees outside with no ambient control. You can use your subcooling to help diagnose it. Low charge will give you low subcooling. A low load will give you normal subcooling. Low ambient give you high subcooling because of colder air over the condenser. Couple of examples of how the system would look in a low condensing temperature with a low charge. Still ambient air of 95. Your condenser split's only 10. It's a little bit low, 105 to 105, no subcooling. It's an iced up evaporator. Still gives you a normal 10-degree subcooling with an iced up evaporator. Okay. High condensing temp causes are going to be an overcharge, high pressure, or low condenser airflow, fan problem, or dirty coil. Find dirty coils all the time, especially on those big train units where they layer the coils together. Those are super fun to clean. High evaporator load will send heat to the condenser. You can use subcooling to help diagnose it. An overcharge is going to give you a high subcooling, or low condenser airflow or high evaporator load will indicate normal subcooling. Another example of a high condensing temperature. Anybody has any comments or questions, feel free to chime in. So if you have a high condenser temp with a high subcooling, it's an indication of an overcharge. If you have a high condenser temp with normal subcooling, it's an indication of a dirty condenser. Summary of changes in condensing temp. If the ambient temperature drops, the condensing temperature drops. If the load on the evaporator drops, the condensing temperature drops as well. If the ambient temperature increases, the condensing temperature will increase. If the load on the evaporator increases, the condensing temperature will increase as well. If the condenser has low airflow, the condensing temperature will increase. And if the condenser has an overcharge, the condensing temperature will increase. You can tell a lot about what's going on with your system just by your condensing temperature and your evaporator temperature, TD. Here's some examples of problems, some easy, some not. No AC or unit not running. Usually this is easy to diagnose. Units are usually off on a high pressure control or low pressure control. Unit runs, but it's not cold enough. It's a little harder to figure out what's going on. But if you use these tools, taking your evaporator TD or condensing TD, it can kind of help point you in the right direction. The unit's running, but it's not cool enough. It's more difficult. May cool, except when it's hot outside. It could be a little low on gas, slightly dirty condenser. The examples will be the difficult type. The symptoms are not bad enough to easily diagnose, such as a slightly low charge or slightly overcharged. Those are times when pulling the charge, weighing it out, pulling a good vacuum, and weighing in a fresh charge is going to be kind of the best bet. Oh, wow, that was a short one. Okay, anybody have any questions, comments, anything to add, anything else you want to talk about? That was a very short slideshow.
Pretty helpful too.
I got something. Anybody ever run into, the carrier units that have the fixed orifices with the liquid header? Run into a restriction with those and have to replace that whole liquid header assembly? Has anybody ever run into that?
I have, not on a carrier unit, but similar situation on a train. They're not fun to replace.
Yeah, that's what I hear, and I see the I see the instructions, so
Yeah,
that's going to be a fun one.
Yeah, it's definitely, you're going to want an extra person, probably 2 torches. Yeah, getting that new header sweated in there, or getting the old one sweated out and the new one sweated in it's quite the task.
Sweet. I look forward to it.
I can hear the enthusiasm in your voice.
Absolutely.
Anybody else? Well, tomorrow morning, Kip is going to be doing the class on water filtration. He's got a good presentation put together about all of our RO systems we use in the Mavericks and just water filtration in general. Some good information to have. I feel like that's kind of something that everybody doesn't really know a whole lot about, the ins and outs of how that RO system works. So be sure to tune in for that one. Okay. Thanks, guys. Everybody have a good day. Be safe out there. Don't freeze to death if you live in these snowy areas.
Have a great morning.
Thanks, Zach.
Thanks, guys.